Yeah, moderator of this webinar from UC Riverside. Welcome to the RGPPS footage section. Our footage section covers a wide geographical area stretching from West Covina to the eastern end of California, and from Temecula to Baker. Today, we are honored to have an IEEE Fellow, Mr. Charles Hemville from Canada, as our speaker today. Thank you for joining us, Charlie. Before starting the presentation, let me introduce the speaker. Charles Hemville is a native of St. Kitts in West Indies. He completed his early education in Jamaica and graduated from the University of Cambridge in 1969. He later earned a Master of Engineering degree from the University of British Columbia in 2000. Mr. Hemville had a distinguished 30-year career with BC Hydro, British Columbia Hydro, retiring in 2005 as principal engineer in protection planning. Since 1977, he has specialized in protection systems for generation, transmission, and distribution equipment. He now runs his own consulting company in power system protection. Mr. Hemville has served as chairman of a power system relay committee in the past and as a distinguished lecturer from the IEEPS. Today, Mr. Hemville is going to cover voltage collapse, which is one of the well-known power system abnormal phenomena. Charlie, where are we?
Thank you, Koji. So today we're talking about the value or the importance of reactive power. And this slide shows what a friend of mine was trying to get the operators of a large power plant to operate their generators at the limits of their reactive power capability. And as some of you may know, it's very difficult to get operators to move close to the limits of equipment because they're worried that it might trip out unexpectedly. So it created this slide which shows how if you need the reactive power from a generator because of a voltage drop, then the voltage will go down, but the generator will try and increase the power, the reactive power that it puts out, but it might not be enough. Often it's not enough, and particularly capacitors and line charging capacitance will give less reactive power as the voltage drops. So the voltage drops even further, we have less reactive support, and eventually what happens, the generators can't supply any more reactive power. They have limiters that prevent them from doing this. And sometimes those limiters don't coordinate properly with the protection. And then the generators trip offline unexpectedly and panic and chaos result. So what I'm going to be talking about today is the importance of reactive power. And another word for reactive power is imaginary power. So just to be clear, I'm talking about using imaginary power to support the power system. I'm not talking about imaginary support to the power system, which this slide shows us. So that's definitely not of any help in supporting the power system. So first of all, I'll describe the phenomenon and then talk a bit about how reactive power mitigates the problem. And if the problem still arises, how we can mitigate it further by controlling the voltage at which the power is developed or delivered. And also in the worst case, load shedding. And if those things don't work, then indeed we might have real consequences, which actually would be blackouts. So here's a problem described fairly simply as I know it. The power developed or delivered to this resistance is equal to the voltage at the delivery point squared times divided by the resistance. So as you reduce this resistance, more and more power is delivered, but the voltage also drops. So at some point, the drop in voltage overrides the drop in resistance, and we find that you reach a maximum amount of power that can be delivered. This occurs when the magnitude of this resistance is equal to the magnitude of the reactance between the power delivery point and the generator. So if this generator is producing power at 1 per unit voltage, then the maximum power delivered will be when this magnitude is equal to the reactive impedance magnitude, and the power delivered will be 0.707 per unit. But people have found that the application of shunt capacitors is very helpful for boosting the voltage and thereby boosting the amount of power you can deliver without doing anything about the transmission system. So it's like very cheap and economical transmission increase just by adding capacitance to the load delivery point. So here we have what we call the PV curve, which is the voltage at the load delivery point times the amount of power that is delivered. And you can see as you reduce the resistance, the amount delivered gradually increases until you reach a certain maximum, and then it decreases again. If you just add some capacitance, then you can deliver much more power, but of course the voltage is far too high when you don't have enough when you're not delivering enough power. So that would not be a very satisfactory state of affairs. And what you might do instead is try and keep the power factor constant. So when you have a low power delivery, you have low capacitance added, and then you add more and more capacitance as the amount of power delivered increases. So this one is with no capacitance at all. This is with constant power factor. And this is another way of increasing the power delivery by adding a series compensation, which is actually decreasing the magnitude of X. So there are various ways to increase the amount of power you can deliver without doing anything about increasing the amount of transmission capacity, which is what a lot of people would like to do. So here we have the constant power factor curve again, compared to the uncompensated curve. And this is the type of voltage that we would like to deliver power at. I show 1 per unit. I know many utilities will deliver power at a slightly different voltage, usually a little bit higher. But just for convenience, I show 1 per unit here. But what happens when you reach the limits of your capability, then the amount of power you can deliver drops off very quickly. In this case, the reactive power is being delivered by a synchronous condenser, but that is more expensive and complicated than just the addition of shunt capacitors. So it's a natural inclination to try and just add more shunt capacitors, but then you get a PV curve that looks something like this, and we say that this is the edge of the precipice. So operators and planners would like to try and operate the power system as close as possible to the limit of capability without actually falling over the edge. And that's been the problem many times when some contingency or multiple contingencies arise. The system falls over the edge and you get a blackout. Also, angular stability can be affected by the amount of reactive power you have. So if we have a voltage at the sending end of a power system equal to 1 per unit, and a voltage at the receiving end equal to 1 per unit, then the maximum power deliverable will be when the angle between these two voltages is 90 degrees. And the maximum amount of power will be 1 over x. But we notice that the voltage in the middle is somewhat less than 1 per unit. So if we just boost the voltage in the middle by adding capacitors or reactive power, no real power coming in at this generator, but just boosting the voltage, we see all of a sudden we can deliver twice as much power through the same transmission system. So there's our reactive power doing its job to support the power system and allowing more power to be transmitted. These are some of the phenomena that can and have happened in various power systems that affect their stability under conditions of low reactive power. So this time frame starts at 100 milliseconds, and some of these things are very fast, like DC controllers, static VAR compensators. Switch shunt capacitors take a little bit of time, maybe 200 milliseconds to come into service. Generators and excitation dynamics generators can increase their reactive power output. And load tap changes take longer to operate. Exciter limiters can allow temporary overload of generators. This is a more frequently these days used option, which of course is not a good option for a firm load that you're trying to supply. But this can and has been used with a certain time frame, maybe 1 to 10 seconds. And then we have the system operator who, being a human being, would take some time to come into play, maybe up to a few minutes. And we also have temporary overload of lines and transformers, which may persist for several minutes. And underlaying it all is my favorite part, which is protective relaying. It can run the full gamut from very high speed to quite slow. So these are all the time frames of the various phenomenon that can affect power systems when you don't have enough reactive power. We see the difference here between a static VAR compensator and a static condenser, where a static VAR compensator just switches capacitance into service as the voltage goes down. So if the voltage level is okay, you may be able to absorb some reactive power if you have shunt reactors. And then as the voltage goes down, you switch your shunt reactors off, switch your shunt capacitors in to try and boost the voltage. But if it still persists in going down, at some stage, you reach the limit of your shunt capacitance. When you reach this limit, then if the voltage wants to go down even more, then the power delivered by the shunt capacitance starts to get less very quickly because it's equal to, it's proportional to V squared. So the shunt capacitance is not as good as the alternative, which could be a static VAR compensator, which has the same shape of characteristic in the control range, but when it reaches its limit, it's only limited by the amount of current it can produce, so it just goes straight down instead of going down as fast as the static VAR compensator. So these are some techniques that have been used to mitigate the problem of declining voltages as the system approaches its limit of available reactive power. Generators, of course, are very handy for wanting to or being able to boost the reactive power. So we see the capability diagram of an example generator here that as the voltage gets lower, it will try to, the excitation system will try to boost the voltage. And we notice actually that it can deliver more reactive power. So along this axis is the reactive power output of the generator. And along this axis is the real power output. So normally operators like to operate in this region here, or even close to 1 per unit. But the generators are capable of boosting the reactive power delivered to the system, and thereby boosting the amount of real power that can be transmitted through your transmission system. So the maximum generator capability available depends on the real power output, as we saw previously. So the higher the real power output, the less reactive power you can put out. It also depends on the terminal voltage, as I mentioned previously. And it also has usually some temporary overload capacity. This would not be true of electronic power sources, but generators certainly can be overloaded temporarily to try and allow any other control actions to mitigate the overload problem. Programmable logic controllers find increasing application in power systems now, as they're trying to measure how close the generators are to their limits and take some control action to reduce the need for reactive power. The field current in the rotor of a generator is a good indicator of how close it is to its limit. So we have here the reactive power from a generator. We see that normally it would be operated in this area here, close to 0 reactive power output. But if reactive power is needed from the generator, it can go up to its limit. The field current on the generator normally would be the limiting factor, although at closer to 1 per unit of, or power factor of 1, the stator current limit may be more important. But if you measure the field current going into a generator, you can tell how close it is to its reactive power limits. And here we have an example scheme which mitigates the problem of voltage collapse by shedding firm load. So we have voltage sensors at 3 different locations in this example scheme. And these voltage sensors are located at different substations so that they're going to show a widespread voltage depression, not just a voltage depression at one location, which could be some contingency, which is not what we're trying to solve here. So this particular scheme looks for low voltages at 2 out of 3 sensors. And if any 2 sensors detect low voltages, and at the same time you have a source of reactive power, megavolts, amps reactive at this substation, if it is close to its limit or at its limit, and both things are true, then you start shedding firm loads. So this is an example of an actual scheme which sheds firm load if those various contingencies happen. I should add that this scheme is installed in BC Hydro, and I actually developed it, but the only time it's worked in anger was a misoperation when it accidentally shed load while they were doing some testing on the system. So it hasn't been proven in anger yet, and not surprisingly, because we wouldn't like any normal operation or normal expected contingency to cause shedding of firm load. So this is really an extreme contingency when you need to shed this load. So mechanically switched capacitors are much more commonly used, and I shouldn't say a great, but it's a economical way to increase the amount of power that you can deliver, as we saw at the beginning, just by boosting the voltage at the delivery point. So these mechanically switched capacitors are cheaper, more economical than static VAR compensators or static condensers. They do take a little bit of time to switch on, but you may have power electronic switches. One person I know who was advocating the use of shunt capacitors with a power electronic switch across one layer. So if the voltage goes down, you just short out one layer of the shunt capacitance, and all of a sudden you get more reactive power out of the remaining capacitors. So these capacitors allow faster sources, namely generators and static VAR compensators, to stay in mid-range to be ready for the next contingency. Some people use programmable logic controllers or other types of smart controllers to coordinate the switching of these capacitors with other faster sources like generators or static VAR compensators. But there's a problem of more complexity, which of course is what always happens when you try and squeeze more juice out of the orange. It gets more difficult, and in case of power systems, more complicated. So we'll look at a few schemes and see how complex these schemes can get. One method of controlling the voltage is just to control the distribution voltage. So allow the voltage to go down, but only to a certain level. And here you have to decide whether you're going to have a brownout or a blackout, because if you reduce the voltage too much, then you'll have a brownout. And if you don't reduce it enough, you'll have a blackout, or you might have a blackout. So some ways of reducing the voltage are blocking load tap changes, for instance, and you get better quality control there, but not so much load reduction if you don't allow the load tap changer to move to its full extent. And so usually if you're using load tap changer blocking, you don't need as much centralized commands to tell it to be blocked. Whereas if you use voltage reduction, which is another method of reducing the demand of the load, this allows lower voltages, but you have to worry about your power quality. And your centralized control devices will know better whether the system really is in trouble and should you reduce the voltage at certain locations to try and reduce your load a little bit. I should mention this business of reducing voltage is quite complicated, because if you reduce it at above or upstream of your load tap changes, and as you reduce the transmission voltage, the load tap change is going to just increase the voltage to your load delivery points, and you won't do any good. So you have to try and control your voltage below or downstream of your load tap changes or your voltage control devices. And in the worst case, you may get to load shedding, which is that scheme I showed you earlier on, where you really don't want to shed firm load unless you have to, unless your system's in extreme trouble. So you can use manual load shedding or the the energy management system, or some sort of automatic scheme. And it's a last resort, but sometimes required. And you may use under voltage, system status, or the margin to collapse. So all of these things are different techniques to initiate load shedding to prevent blackout. Some of the things that would be needed, for instance, are very accurate relays and transducers, because as we saw, the voltage collapse point happens very close to normal or required voltage levels. So you need very precise measurement of voltages before you take any, I nearly said catastrophic, but I should have said extreme action to shed firm load. So you would always use, if you're measuring voltage, you'd always use three-phase voltages and make sure voltages were low on all three phases. And also the you need a window so you can be sure that the voltage just didn't disappear because you switched the voltage measuring device offline. As I showed you in that scheme earlier, you need communication systems because you'll be measuring the voltages at different locations. Another possible problem is overshedding. So your load shedding scheme is going into service. As long as it goes in before load starts to drop off just of its own free will, so it needs to start operating very close to normal operating voltage levels. Otherwise, you're in danger of overshedding because your automatic scheme is working at the same time as load is just falling off the system due to low voltages. Often you'll have load being shed in stages, either definite time or inverse time. So the lower the voltage, the faster shedding. In many cases, you'll have manual arming of these load shedding schemes because of that danger, as I showed you before, where we had a load shedding scheme and it was armed and it started shedding load, but it was only undergoing test. So the controls that you use to make sure that the load shedding scheme doesn't operate unexpectedly are very important. I'm going to show you one incident now, which some of you might be aware of, which was triggered by a sunspot. And just to show you the size of the sun, I superimposed here the relative size of the Earth. Of course, it's not so close as to be in the flare from the sun, but it's just to show you the relative size. And we consider a blackout in Quebec in 1989. So in this case, at this blackout, they had remote generation far away and long extra high voltage lines supplying loads in the south. And the voltage was being supported by static VAR compensators, which, as I showed you, can push up the voltage in the middle of the transmission system and allow more power to be transmitted. But then they had a solar storm when the sun spots, or the solar flares on the sun started inducing geomagnetic currents. These are very low frequency currents that can be induced by the changing magnetic field during solar activity. So these geomagnetic currents caused harmonics. Cause harmonics which caused some static VAR compensators to be tripped offline, and a blackout ensued. So here we have a diagram of the network. So down here at the south end is where Montreal is, the big load center. And up here at the north, far away, are the major generating stations. And also from the northeast, some more heavy-duty generating stations. So these are all extra high voltage transmission lines, 735 kV, I think. And these little squares are various shunt capacitor or static VAR compensators, which are boosting the voltage in the middle of the transmission system. And here we see how fast this phenomenon can increase. So at this moment in time, and if we look at the bottom scale, we see each division is only 1 second. So the static VAR compensators started tripping offline, and at this point, the last static VAR compensator tripped offline. And these are the angles between two stations. So one of them is curve number 1 is between Arnaud to Boucherville, and the other one is from LG2 to Boucherville. So if we go back, we can just look at these. So up here, I think we have Arnaud to Boucherville is down. There's Boucherville down there. I don't see Arnaud. But anyway, it's the angle between these sources and the Boucherville, which is the delivery point. So they start to increase as these shunt capacitors trip offline. And we can see just in a few seconds, the blackout ensues. So what we've learned from this is that the imaginary power, the reactive power from these shunt capacitors have really boosted the transmission capability. And if they're not there, then they can't do their job. In the case of the Western states in the United States, in 1996, there were a few severe blackouts. In this one I'm describing here, there was a short circuit on one 345 kV line, and the parallel line also tripped out unexpectedly due to a hidden failure. And there was 2,000 megawatts of generation lost. There was what's called a special protection scheme, which tripped this deliberately tripped the generation offline because of the sudden loss of these two transmission lines. So the generation being tripped offline was intentional, but the voltages started to decline very quickly as the lines became heavily loaded. As often is the case, a protective relay operated unexpectedly when the power system was under stress. So this zone 3 is a transmission line protective relay, which tripped a 230 kV line. And then some generators at McNairy Generating Station also tripped offline. So in that case, nearly 12,000 megawatts of generation was lost. So that was a very severe event. And here we see the voltage at a certain point in the station, in the system, where the voltage was being monitored. And this here is 525 kV. So it's a 500 kV transmission system, and it's operating above 525 kV for most of the time. And then this scale down here is in seconds. So this is 5 seconds from this point to this point. So within 10, 15, 20, 25, all of a sudden you got a very fast voltage collapse. But the interesting thing to note is that the voltage was being maintained at or above the minimum voltage they wanted until the very end. So really, they fell off the edge of the precipice very quickly. This 230 kV line tripped at this location, and the other generators tripped offline shortly after. So my wife and I were driving through, was it Colorado, or we were driving back from Colorado to Vancouver, and I saw a sign saying McNairy Generating Station. So I said to my wife, we've got to stop here and look at this, because it's a very important generating station that was part of a very significant blackout in 1996. So we stopped, and sure enough, as I got there, they opened the gates and started spilling water. And I said to myself, well, you didn't really need to welcome me in such a grand manner, but I was happy to see the water spilling. And that was a significant point in our journey back to Vancouver. So on the 14th of August in the year 2000, there was another incident, this time on the east side of North America. And in this case, there was barely enough power, imaginary power, all afternoon. And then there was a major generator at East Lake Power Station, which tripped offline when it was needed most. But the transmission voltages were fairly well maintained, and this hid the edge of the precipice. So this is what I'm saying, that the precipice is often very hard to anticipate. So at 6 minutes after 4, the blackout started, and by 13 minutes after 4, the 61,000, nearly 62,000 megawatts of load had been lost. And here we see the reactive power output at East Lake Power Station, and we see from all afternoon, from 11 a.m. until 1 p.m. or 1:30 p.m., the voltage was not was being maintained okay, but the reactive power of these generators was being stretched to its limit. And this is what I said, these generators were no better than the McNairy generators. They tripped offline when they were needed most. The operators tried to put it back online, but it was not successful, and the blackout ensued. One of the questions I had when I made this presentation some time ago is, Charlie, I've heard of round rotor generators and salient pole generators, but I never heard of McNairy generators. What kind of generators are they? So that's when I added this slide showing the McNairy power station, so you would know what type of generators the McNairy generators were. And we see the measured voltages on just before and during this blackout. You can see this is 95% of nominal voltage, and only at one station did the voltages drop below the 95% mark. So again, the edge of the precipice was not very easily seen just by measuring voltage. And here we have some voltages at various locations just before the blackout. These are various substations in the network, and we can see how they're above 95% of nominal at most locations until very close to the limit or to the end. In south of Sweden, in Denmark, in the same year, 2000, there was a big blackout where there was a loss of a large generator, a 1,200 megawatt generator. And then 2 other generators tripped offline very quickly after, and they had a voltage collapse in southern Sweden and in Denmark. And here we look at the voltages at the north, which was not blacked out. So these are the pre-contingency voltages above 400 kV. But we can see how the voltages are very close to normal over most of the time until just prior to the collapse. In this case, the collapse took considerably longer than some of the other incidents I showed you, and these time steps are in increments of 10 seconds. So it took quite a long time before the blackout occurred, but eventually the blackout occurred. The south part of Sweden and Denmark both went black, but the north part, the voltage rose again and stayed as a pre-contingency. This is a case from Peru, which I like to show because it's a real life example of a PV curve that I showed you at the beginning of the power being delivered can increase and then be reduced. So in this case, what happened was this transformer tripped offline suddenly, and the power that was going that way had to go this long way around like this, and the voltage started dropping, and eventually the protection at this end of the transmission line tripped offline. But because it was a modern protective relay that monitored or recorded the voltages and currents that it was seeing, we got a recording of the voltages and currents at this point. So we see here the three-phase currents gradually getting bigger and bigger, and the three-phase voltages gradually getting smaller and smaller until the line trips, and then the current goes down to zero, and the voltage goes back up to normal or even slightly higher. So it's interesting. You can use these traces and plot the power with respect to time that is being delivered along this transmission line here. And we see here that as time goes on, we're moving along this PV curve, and eventually the system goes black at the end of the transmission line. So that's the only real life PV curve that I've seen, but we looked at some theoretical ones at the beginning of this presentation. So what we can conclude from that then is that the system planners, we want them to anticipate the problem offline. So they want to plan for whatever contingencies they can think of and determine what control actions might be taken. In the extreme case, of course, shedding load. They can diagnose the problem online by measuring the output at various locations and the voltages at various locations. They can allow temporary overload of various pieces of equipment, particularly generators and maybe shunt capacitors, but shunt capacitors very little. You can try and control load tap changes to see if the load can be controlled a bit, but there's not a lot of scope in that. Of course, the ideal solution by the engineers is to increase transmission, but this is not the ideal solution by the rest of the world. So the engineers get outvoted in this case, and they try and the planners try and use other solutions, which are, for instance, to mix reactive support, whether it be local generation or shunt capacitors or static VAR compensators. So have a variety of reactive supports. And in the last case, or the final case, then all you can do is shed load. So these are some references I'd like you to feel free to look at. Koji, I think you will be making this available to the participants so they can see all these references, will you?
Oh.
Sorry, can't hear you, Koji, but...
Yeah,
Maybe.
I'm online.
Yeah, I got you now. Sorry, what did you say?
So here is the list of like available documents
Yes,
regarding the voltage collapse. Okay.
yes,
Yeah, I think for universities, we can download most of the documents through website, IEEE Explorer.
yes, yes.
But
Uh,
for example, in the case of PES technical report, I think we have to be a member of, the member of IEEE PES specifically.
yes, to get it free. Yes,
Yeah, these are
but
really helpful.
yeah. Oh, I forget. Of course, you are not at the same location as all participants. So, uh, yes, most of these PES publications, if you're not a member of PES, you do have to pay for them. The only one that's free, which I think is the best one, is this one at the bottom, where I've provided the link, and that's produced by the Power System Relaying Committee. And I like it very much because I was the chairman of the working group that produced that.
Awesome. So it is free of charge or we
Yes,
have to
yes.
pay? Oh,
No,
okay.
no, it's free, this one.
Perfect.
These other ones like Western Protective Relaying Conference, this is free to the attendees. So you would have to find somebody who attended that conference. Many of the protection engineers on the west side of North America do go to that conference. So if you know someone who's a protection engineer, they should be able to find that for you.
Was
This
that sponsored by IEEE or other organization?
No, this is only sponsored. Oh, I think it's available now from the conference website. You can
Okay,
find it. Yeah.
perfect.
These other ones are transactions. You have to be a member of IEEE. Transactions. Technically, you have to be a member of PES to get that one for free. And transactions. So all the transactions papers are only available at a cost unless you have some sort of membership. Yeah, so I could take questions now. Be happy to answer any questions.
Oh, yeah, thank you for the nice presentation. And then Charlie, can you open the chat window? We
Oh,
have one, yeah, we have one question
oh,
from
sure.
audience.
Not sure how to open the. Maybe you could just ask it for me, Koji.
Or I can read it.
Yes, please.
Okay, so shunt capacitors have a reputation of failing, often blowing internal fuses. If you take into account monitoring and replacing these capacitors, would they still have an economical advantage over other methods? This is the question.
Yeah. Oh, definitely. Yes. The answer is yes. So when you compare it to the alternative, which is building new transmission, then there's no contest really. So as the transmission lines or transmission systems become loaded more and more heavily, most planners will take advantage of the economics of shunt capacitors. Now, as to their reliability, I think the person who asked that question just has a bad experience. I wouldn't say that they are as unreliable as the questioner indicates, but I can't say why he has had this bad experience. He or she.
Yeah, thank you. So by the way, so in the case of voltage stability issues, one of the main causes must be how much the loads, the customers consume reactive power. And then, so in the past, we have lots of induction motors in the customers area. And then eventually we consume large amount of reactive power. And then we need sufficient amount of reactive power support from shunt capacitors or synchronous condensers or generators, whatever. But now I think we have increasing number of inverter interface loads. So essentially they do not consume reactive power. They essentially consume active power. So if we consider the change in the load structure in the future, do you think still we have significant concern about the potential voltage collapse in the future grid?
Uh, I think the key is the sentence, if we consider the change in the future. And my answer is there's still a lot of installed equipment which doesn't have those converter or inverter interfaces. So the percentage of modern loads which can control their reactive power is going to grow relatively slowly, I think. But yes, it will help, I'm sure. So the availability of these types of loads definitely will help, but I don't think they will overcome the problem of increasing demand on the transmission system to deliver or send more power along it. So yes, it will help, but not, in my opinion, enough to mitigate the problem. But of course, planning and operations are the two main methods for mitigating the problems, because these problems that I describe usually only happen under multiple contingencies, which are not considered in the planning process. And that's why they're rare, but they do happen. So my intent was just to show that this imaginary power is a very important part of power systems, which sometimes neglected because they don't produce or use any real power.
Yeah, thank you. Yeah, I totally agree with this point.
Yeah.
The Japan had an experience on voltage collapse in 1980s. And then at that time, we started to install like a synchronous condensers additionally. But after that, I think we completely shut down all of the synchronous condensers nowadays and switched into like a SBC, static bar
Yeah,
compensators, or STATCOM, due to the mainly like maintenance issues.
I see.
Yes,
Yes,
but
yes.
so now we can ask, for example, the renewable energy sources to provide reactive power other than the shunt capacitor or synchronous condensers. And then there are kind of like updating the grid code requirement regarding reactive power support nowadays. And then
Ah,
do you think the reactive power support from renewable energy sources like wind and solar are kind of trustable? I mean, they're reliable because these are intermittent resources. So I'm not so sure it is not kind of trustable.
I see. Well, remember we have two types of modern sources. One is wind power and the other is solar power. So uh, I'm not familiar enough with the solar power to say what it could do in the daytime, even if there's no sun. I'm sorry, I don't know if it can still produce reactive power, but certainly the utilities who are in charge of planning the power system, when somebody wants to connect, this is a new one on me. Of course, I've been out of the utility business for 15 years now. And in those old days, we never asked anything about the reactive power capability, only the real power that it wanted. So I'm interested to learn from you, Koji, that nowadays utilities will ask or even require certain reactive power capabilities from people who want to connect to the system. That's a good idea, because theoretically it doesn't cost very much, and practically it makes a big difference.
Okay. Yeah, we have one comment from audience regarding this question. So the wind and solar in ERCOT, which means Texas, are tested for performance on voltage control nowadays. So I think it depends on the capacity and also the connected voltage level, I guess. We cannot expect the kind of like a reactive power support from residential PVs. So, although the residential PV can support reactive power to the grid, but the location is very edge of the grid. So that is not propagated to the main grid, which means transmission system. So, but if we have like a very big wind farm or like utility scale PVs, and then if they are directly connected to the sub-transmission grid or transmission grid, I think we can expect some like a reactive power support from the wind and solar. So it really depends on the connected point of the voltage levels and then also capacity, I feel.
Yeah, I agree. And actually, I think the questioner also agrees with you. He added a comment, or he or she added a comment saying they were talking about further up the system than just the distribution load.
Yeah, so like a 40 gigawatt, 30 gigawatt solar. So yeah, that really makes sense.
Yeah.
But in the case of voltage drop event, like the system fault, and then not only the loads, but also the solar or winds can be disconnected at the same time. And then if the load recovered right away, and then if the renewable energy source disconnected for a while, and then the apparent load drastically increase right after the event happened. And then, of course, we need sufficient amount of reactive power support from the grid. And then if we do not have enough reactive power, and then, of course, we have the potential voltage collapse issue, I feel. So, we do not know how much the wind and solar can stay connected. Of course, it depends on the capability of the fault right-through requirement.
Yeah.
But not all of the winds and solars satisfy this requirement nowadays. So,
but I thought they were supposed to, Koji. Yeah, they're required to. If and I don't know, but I assume they are tested to make sure that they can. Yeah, I see. Greg Peston says they
so
have these requirements.
the new one is definitely true. But we have already installed bunch of renewable energy sources more than 10 years ago.
Yeah,
and then we do not know these performances.
Correct. Yes, and I am aware of loss of some of these sources in the BC hydro system. Older sources, older events, older types, which after the voltage depression, they did get lost. Yeah.
Okay. But anyway, time is almost up. So Charlie, thank you for the nice presentation again. And then also, folks, our next webinar will be held on April the 8th. We will invite Dutch speaker, and then the topic will be the grid operators challenge in the Netherlands due to energy transformation. And then the flyer will be uploaded to the IEEE tools and then the IEEE 30 section website when it is ready. So please stay connected and then enjoy the rest of your day. Thank you for joining us.
We have one question, Koji, about will the recording be posted?
Oh, yes, of course. So, but by the way, can we use your slides if possible? Especially the last slide is really helpful for further reading.
I don't think I can give you those slides, but I could. First of all, I can give you a printout of of all the slides, and I did. Just the one I sent you was 6 slides per page, but I can send you maybe 2 or 3 slides per page.
Yeah, especially the last slide must be very helpful.
Oh, okay.
The last slide, yes,
yeah,
because you
yeah.
have the list
Sure.
of publications.
Yeah, Jane Preston says he's screen captured. Yeah, but I'll send you the last slide by itself, Koji, directly.
Perfect. Thank you.
You're
Anyway,
welcome.
this webinar was recorded, and then it will be uploaded to the Agri-Food section PES website shortly.
Yeah.
So yeah,
Well,
thank you for joining us.
inviting me. It was a pleasure.